So this problem says a 50 turn coil has a diameter of 15 centimeters. So 15 centimeters is half a foot. The coil is placed in a spatially uniform magnetic field of magnitude 0.5 Tesla. So that's a pretty strong field. So that the face of the coil and the magnetic field are perpendicular. Okay, so there's the coil and there's the magnetic field. Find the magnitude of the EMF induced in the coil if the magnetic field is reduced to zero uniformly in 0.1 seconds. Okay, so we'll just do part A. Okay, Mr. Faraday tells us that the induced EMF in the coil. Okay, by the way, so let's figure out the direction of the current first. Okay, as the magnetic field decreases, which way will the current be induced? Okay, so Mr. Lenz says if the field decreases, what the induced current wants to do is oppose that change. So it wants to produce a magnetic field in that direction. So the induced current will be like that. Okay. So make sure you understand that. Okay. If the magnetic field is decreasing, okay. All right. And that's what this negative sign is about. So the induced voltage is rate of change of negative rate of change of that. Okay, we are just going to find the magnitude of the induced EMF. We have the direction, so now we'll find the magnitude, which is d phi by dt. D by dt, and the magnetic flux is the number of loops times the area times the magnetic field. In our problem, what is it that's changing of the three factors?
The number it's spinning.
No.
The field is changing.
The field is changing, okay? All right. So the induced EMF is NA okay, you guys understand? Yeah. 50 turns, area is pi r square. Radius is 0.075 centimeters, 0.075 meters square. And change in magnetic field is 0 minus that, but we are taking the absolute change, so it changes by 0.5 Tesla to 0.1 second. So the induced voltage would be and this will work out in volts. What's that?
4.418.
All right, 4.418 volts. Okay, so here's the deal. Okay, so when you turn off a magnet, that's called quenching a magnet. And let's say if you turned it out in 0.01 second, the voltage induced would be 44 volts. Okay, and if this was a wire that was that belonged to some circuit, turning off this magnet could turn on some other machinery. Okay, so you don't, if you have a strong magnetic field, you don't turn it off fast. So MRI machines and all that, you turn them off slowly. Okay. MRI machines have magnetic fields of 2 Tesla and so on. Okay. Did you guys understand that? this problem says a single turn circular loop of wire of radius 50 millimeters lies in a plane perpendicular to a spatially uniform magnetic field. During a 0.1 second interval, the magnitude of the field increases uniformly from 200 to 300 millitesla. Determine the EMF induced in the loop. If the magnetic field is directed out of the page, what is the direction of the induced current? Okay, so there's the magnetic field. And so there's the loop. All right, so the magnetic field is increasing. So what should be the direction of the induced current? Clockwise. Okay. So what you want to do is the induced magnetic field should be in the opposite direction. Okay. And so the current is clockwise. Okay. All right. And again, Mr. Faraday tells us that del phi by del t, the magnitude of the induced EMF is area is constant, it's B that is changing. Radius is 5 centimeters, 0.05 meters. And change in magnetic field is 100 millitesla. And this change happens over 0.1 seconds. So now the induced EMF is, so this guy is essentially 1. So that's 10 to the minus 2, that's 1. Okay. Yes, 7.85 into 10 minus 3 volts. So in the induced EMF is 8 millivolts. Okay. Any questions on that? Okay, let's do a couple of these. Use Lenz's law to determine the direction of the induced current in each case. All right, so the magnetic field here is coming out of the paper. Okay. And if you move it to the right, the flux coming out of the paper increases. So the induced current needs to decrease it. So the induced current would be clockwise. Okay. Yeah. So to me, this thing appears, the ring is actually perpendicular to the okay, so the field is coming out and the ring is perpendicular to the plane of the ring is parallel to the magnetic field. So there's no induced current there. In this case, B is decreasing, so you have to produce a field coming out of the paper. So induced current will be like that. Okay. All right. This is a coil of 1,000 turns encloses an area of 25 centimeters squared. It is rotated in 0.01 seconds from a position where its plane is perpendicular to the Earth's magnetic field to one where its plane is parallel to the field. Okay, so let's say here's the Earth's magnetic field. So okay, and then so here's the new configuration. Okay. So this is the area vector, and there's okay. Parallel to the field. If the strength of the field is 6 times 10 to the minus 5 Tesla, what is the average EMF induced in the coil? Okay, again, EMF is del B times area delta T. Again, when you're turning the coil, you're not changing the area. All you're changing is the magnetic field that, okay, well, the flux that goes through. So right now the flux is B times area. Now the flux is 0. Okay. So, oh, by the way, there's 1,000 turns to the coil. So this was the initial flux, and the area is 25 10 to the minus 4 meters squared. All right, so that's 10 to the minus 9, 10 to the minus 6, and 6 times 25 is 100, 9, 6, minus 4, 150 times 10 to the minus 4 volts. 15 into 10 minus 3 volts. Okay, so the induced EMF is 15 millivolts. Okay. So you took a 1,000 turn coil and turned it within 10 milliseconds in the Earth's magnetic field, and the voltage induced was 15 millivolts. Okay. Okay, this is sort of the reverse of the problem we saw. If you guys remember, in turning satellites, you had torquers in the presence of Earth's magnetic field. Now, what you do is when you want to turn a satellite, you pass a current through this thing, and that turns in the Earth's magnetic field, and the satellite turns in the opposite direction. Okay, so here's a magnetic field coming out of the plane of the paper, and you move a rod in the presence of this magnetic field. This becomes a battery. Okay, the rod shown is in the accompanying figure is moving through a uniform magnetic field of strength 0.5 Tesla with a constant velocity of magnitude 8 meters per second. What is the potential difference between the ends of the rod? Okay. The EMF induced is BLV. Okay. And that's 0.5 Tesla. The length of the rod is 5 centimeters. And the velocity is 8 meters per second. So that's 4 times 5 is 20. Okay. So 0.2 volts. So 8 meters a second is about 20 miles an hour. You move this thing 20 miles an hour and it's only about um, 0.2 volts. See this kind of stuff. So if this was a plane flying through the Earth's magnetic field, the plane develops a voltage across its wingtips. You know. Where else would you, in a helicopter, the blades rotating, you would, if, I don't know, are they metal? Yeah. So they'll develop voltage across them. Yep. Okay. All right, so we'll a 25 centimeter rod moves at 5 meters per second in a plane perpendicular to the magnetic field of strength 0.25 Tesla. The rod velocity vector and the magnetic field vectors are mutually perpendicular. So, okay, as indicated, calculate the magnetic force on an electron in the rod. Okay, so the magnetic force on the electron in the rod. So the electron is there's an electron moving in this direction, and what would be the force? The force on a positive charge, there's the magnetic field, V cross B. V cross B would be a force in that direction, so the force on the electron is downward. Okay. And what would be the force? The force on the electron would be QVB. So the charge of the electron, the magnitude of the force is that there's the charge of the electron. What is the velocity? Oh, they don't give you the velocity. What's that? So they just want you to calculate the magnetic force on an electron in the rod. Oh, 5 meters per second. So the magnitude of the force is okay. So that's the force, and the electric field in the rod. So the rod acts like a battery, and the force on the electrons is there, so the electrons collect here. And what is the voltage of the battery? It's BLV. Okay. So the EMF of the battery, and the EMF of the battery is, there's the length. EMF of the battery is the electric field times the length. So the electric field inside the battery is EMF per unit length, which is BV, which is 0.25 Tesla times 5 meters per second, 1.25 volt per meter. So what this number tells you is if the rod was 1 meter long, the voltage across it would be 1.25 volts. Okay. And the potential difference between the ends of the rod would be that. Okay. So EMF would be BLV. (25 centimeters). So the EMF is 0.31 volts. What should be the speed of the rod if the potential difference is 1 volt? So if for 5 meters per second, it's 0.31 volts. So if you want 1 volt, you can calculate the velocity, and you can see that if you want 3 times the voltage, the velocity should be 3 times as much. All right, guys, I'll do one more problem and then we'll get done. All right, well, all right, so this problem and this problem are similar. Okay, so I'll do this problem. So the current in a long solenoid of radius 3 centimeters is varied with time at a rate of 2 amperes per second. Okay, so here's a solenoid, and here's wire going around the solenoid, and this current is changing. Two amperes per second. Okay, what does this current do? It produces a magnetic field inside the solenoid. Okay, so as the current is increasing, the strength of this magnetic field is increasing. Okay. If you guys look up your notes from a previous chapter, the magnetic field is given by mu n I. N is the number of turns per number of turns of wire per meter. And so dB by dt is mu naught n di by dt. Okay, so that's how this magnetic field is changing. Okay. All right. A circular loop of wire of radius 5 centimeters and resistance 2 2 ohms surrounds the column. Okay, so now what you have is another wire that surrounds this guy. The EMF induced in the the EMF induced in that wire is d phi. Okay, the flux through this thing, the magnetic field is only in this area. So the flux through this thing, it's this area times the magnetic field. Okay? This area times the magnetic field. And the area is not changing, it's the magnetic field that's changing. So pi r smaller square times mu naught n di by dt. Did you guys understand that? Okay, so here is a loop. So the EMF through this loop is B, rate of change of B times this area. So if the loop was bigger, would the EMF change? It would be the same. It doesn't matter as long, once the loop is outside, the EMF would be the same, okay? Okay. All right, so the induced EMF is pi the radius of the radius of the solenoid, the current in the solenoid of radius 3 centimeters. So 0.03 meters square. Oh, the circular. Find the electrical, okay. They haven't given n in this problem, okay. N was not given, so n assume. We'll assume n, and let's say 500 turns per meter. Okay. So, and then mu naught n di by dt. Okay. Mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. N is 500 per meter, 500 turns per meter, and di by dt is 2 amps per second. Again, n was not given, and we are assuming n. All right, so this is the induced EMF in this circular coil. And again, like we said, no matter what the radius of that thing is, as long as you're outside the solenoid, the induced EMF will be the same. Okay? So what we're saying is the current in this solenoid wire is changing at 2 amps per second, and you're inducing a current in this coil. So let's see. This problem is this is the situation. So there's the solenoid, you're changing the current in the solenoid, and you're calculating this induced current in this loop. Okay, so that's what we're doing. Okay, so the EMF induced is this. Okay, let's do powers of 10. That's 10 minus 4, 10 minus 11, 10 minus 9. Okay, so pi into 9 into 4 pi into 5 into 2 into 10 to the minus 9 volts. Okay, so
I got 3.5 times 10 to the minus
6.
6, yeah.
What 3 point?
3.55.
Okay, so 3.55 microvolts. Okay. And now if this loop of wire has a resistance of 2 ohms, the current induced in that loop would be the voltage divided by the resistance, which is okay. So 1.77 microamps. Okay. All right, guys, we'll stop here.